Welcome, everyone. Today, we are looking into the topic of carbon and its compounds, and how covalent bonds are formed. Let's start by asking the question: what is carbon? Carbon is a fundamental element for life on Earth, found in the atmosphere, Earth's crust, and all living organisms. It is a major component of many fuels, including wood, coal, charcoal, coke, petroleum, natural gas, biogas, and marsh gas. It can also be present in a range of compounds, such as carbonates and hydrogen carbonates. Furthermore, it is present in its free form, including in diamonds, graphite, and fullerenes. Carbon has an atomic number of 6 and an electronic arrangement of 2, 4. It has 4 valence electrons, which are able to form covalent bonds with other atoms, a process known as tetravalency. This allows carbon to create strong bonds with other elements, creating new compounds that are essential for life in many industries. If these bonds were not formed, many of the compounds we rely on would not exist. Covalent bonds are a type of chemical bond that occurs when two atoms share electrons. The electrons are shared evenly, thus forming molecules with a stable structure and properties. For example, in a hydrogen molecule, 2 hydrogen atoms share a pair of electrons, forming a single covalent bond. This distribution of electrons is what creates the molecular structure and is essential to comprehending chemical reactions. Covalent bonds are formed between nonmetal atoms when the atoms share electrons. Nitrogen has an atomic number of 7 and an EC of 2.5, meaning it needs 3 extra electrons to become stable. This is why nitrogen atoms form a triple covalent bond when put together. Oxygen, with an atomic number of 8 and an EC of 2.6, requires 2 extra electrons for stability, thus a double covalent bond is created. Nitrogen and oxygen molecules can then be combined to form various molecular compounds. Carbon atoms have a remarkable quality called catenation, which allows them to form covalent bonds by sharing electrons with other carbon atoms. This enables them to form particularly long chains, branched chains, and closed rings, leading to a wide array of compounds. Furthermore, carbon atoms can form covalent bonds with atoms from other elements, such as hydrogen, oxygen, nitrogen, and halogens, allowing for an even broader selection of compounds. It is this versatility of the carbon atom that allows for the vast number of carbon compounds. Hydrocarbons are compounds composed of carbon and hydrogen atoms. These compounds can be either saturated or unsaturated. In the case of saturated hydrocarbons, the carbon atoms are connected with single covalent bonds. An example of a saturated hydrocarbon is an alkane, which is identified by a suffix of -ane. As an example, methane is composed of 1 carbon atom and 4 hydrogen atoms, all with single covalent bonds. Similarly, ethane consists of 2 carbon atoms and 6 hydrogen atoms, with single covalent bonds between them. Hydrocarbons are organic compounds composed of hydrogen and carbon atoms. These molecules can be saturated or unsaturated, depending on the types of bonds between the atoms. Unsaturated hydrocarbons are hydrocarbons with a double or triple covalent bond between 2 carbon atoms. Examples include alkenes, like propene, C3H6, and alkynes, like ethine or acetylene, C2H2. Unsaturated hydrocarbons are distinguished by their suffixes. Alkenes use the suffix -ene, and alkynes use -ene. Isomerism is the property of having different structural formulae with the same molecular formula. This can be illustrated with various isomers of butane, C4H10, and pentane, C5H12. For example, Butane has two isomers, normal butane and isobutane. Normal butane is represented by the molecular formula H, C, 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 H, H, C, 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 H, whereas isobutane is represented by H, C, H, I, H, I, H. Similarly, pentane has three isomers, normal pentane, isopentane and neopentane. Normal pentane is represented by H, C, 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 H. Isopentane is represented by H, C, H, I, H, I, H, and neopentane is represented by I, H, H, C, H, I, H. Atoms of different chemical elements have the ability to combine in various ways and create molecules, which determine the properties of a carbon compound. A great influence on carbon and its compounds comes from the bonds formed between atoms, and the most significant being covalent bonds that are created through the sharing of electrons. Functional groups. Atoms are groups of atoms that give the carbon compound its chemical properties, can take the form of halides, alcohols, aldehydes, carboxylic acids and ketones. Halides often contain chlorine or bromine atoms, while alcohols end with OL, aldehydes have al at the end, carboxylic acids will end with OIC acid, and ketones with 1. All these functional groups significantly contribute to the properties of carbon compounds as well as their reactivity. Carbon compounds possess an outstanding property in their ability to form covalent bonds. This occurs when two atoms share electrons and allows for the formation of differently or identically shaped structures depending on the atoms in question. An example of this is the homologs series, a group of carbon compounds with similar structures, chemical properties, and which differ from one another by a CH2 group. Examples of this series are alkanes, alkenes, and alkynes with a molecular formula of CnH2n plus 2. Alkanes, ending in -an, are composed of methane, ethane, propane, butane, and pentane. The molecular structure of these compounds can be represented using a table to indicate the arrangement of atoms. The strength of covalent bonds is evident here and is a fundamental factor in many natural and manufactured processes. Alkenes are a form of hydrocarbon with carbon atoms linked using a double covalent bond. Their general molecular formula is CnH2n, with most alkenes having 2 to 4 carbon atoms. These hydrocarbons are also referred to as olefins. Examples of alkenes include ethene, C2H4, propene, C3H6, butene, C4H8, and pentene, C5H10, all distinguished by the double covalent bond between two of their carbon atoms. This bond is signified by the suffix -ene added to the hydrocarbon's name. Alkynes are hydrocarbons with a carbon-carbon triple bond, and the general molecular formula for these compounds is CnH2n-2. The three most common alkynes are propyne, C3H4, ethyne, C2H2, and butyne, C4H6. These alkynes are named by adding the suffix -ene to the corresponding alkane. Carbon compounds are highly versatile and essential in our daily lives. Combustion is an example of how we can use carbon compounds. Combustion is a chemical reaction when molecules combine with oxygen from the air, releasing heat, light, and other products. For instance, burning methane, CH4 with oxygen produces carbon dioxide, CO2, water, and heat, usually accompanied by a flame. Oxidation is another significant process making use of carbon compounds. Oxidation is a reaction between a compound and an oxidizing agent, such as alkaline potassium permanganate or acidic potassium dichromate, with the resulting products varying. Alcohols are often oxidized to form carboxylic acids, with ethanol for example being oxidized to ethanoic acid when heated with alkaline potassium permanganate. Oxidation and combustion processes are essential for everyday life, affecting the fuels used to power our cars and many components of medicinal drugs. Hydrogenation is the process of adding hydrogen to an unsaturated hydrocarbon to create a saturated hydrocarbon. This process is used to convert unsaturated oils and fats into saturated oils and fats. Additionally, saturated hydrocarbons can also undergo substitution reactions with halogens to form substitution products. An example of this is methane undergoing substitution with chlorine in the presence of sunlight. Ethanol is a key carbon compound that appears in the form of a colorless liquid with a pleasant smell and burning taste. It can dissolve in water and undergoes reactions with sodium to form sodium ethoxide and hydrogen, and with concentrated sulfuric acid to generate ethene and water. Ethanol is commonly employed to produce alcoholic drinks, as a solvent, plus in the fabrication of medical concoctions like tincture iodine, cough syrups, and tonics. The slide you are hearing about is all about the properties, esterification, and saponification of ethanoic acid. Ethanoic acid, also known as acetic acid, is a colorless liquid that has a pungent smell and a sour taste. It is soluble in water and, when a solution of 5 to 8% ethanoic acid in water is used, it is called vinegar. Esterification is the reaction between ethanoic acid and ethanol which produces ethyl ethanoate. When ethyl ethanoate reacts with sodium hydroxide, it goes through a process called saponification, and it produces sodium acetate and ethanol. Finally, ethanoic acid reacts with bases to form salt and water, and it reacts with carbonates and hydrogen carbonates to form salt, water, and carbon dioxide. That was an overview of ethanoic acid and its compounds. When soap is added to water, the combination of its hydrophobic and hydrophilic components forms spherical structures called micelles. The hydrophobic part of the molecule, which is typically composed of long-chain carboxylic acids such as sodium stearate, C17H35-CuNa, is soluble in oil and grease, while the hydrophilic part is not. This results in the oil and grease being trapped into the micelle, creating an emulsion. The emulsion can then be washed away with water, taking the dirt and grease with it. Detergents are long-chain sodium salts of sulfonic acids and are very efficient for cleaning. In comparison to soaps, they have the advantage of not forming insoluble precipitates of calcium and magnesium salts when used in hard water. Detergents have a better cleaning power than soaps, although soaps are biodegradable and do not cause pollutant. On the other hand, some detergents are non-biodegradable and must be used correctly in order to prevent pollution.